Today, we're going to look at probability events. When all outcomes are equally likely, we can calculate the theoretical probability of an event A in the sample space. We can notate that here below. I've written P of A, or the probability of event A, is going to be equal to the number of favorable outcomes, the ones that I'm looking at, divided by the total number of possible outcomes. That's how you find any probability. We're going to start off by reviewing before we dig into any new material. So let's start with number one. You roll a standard number cube once, like a playing die in a board game. What is the probability of rolling an even number? I'm going to use that same probability notation here. The probability of rolling an even. Our possibilities here are 2, 4, and 6. Out of all of our possibilities, rolling a 1, 2, 3, 4, 5, or 6. Now, this is not going to tell me my probability yet. How many possible outcomes are there in that numerator? There was 2, 4, and 6. There are 3 total possibilities of favorable outcomes out of how many total possible? There are 6 sides to that die, 6 options, 1 through 6, and then we could simplify to 1/2. The probability of rolling an even number is 1/2 or 50%. You can use a fraction or a decimal or a percentage to write a probability. Number 2, Camilla owns a small business selling used books. She knows that in the last week, 40 customers paid cash, 16 customers used a debit card, and 39 customers used a credit card. Based on these results, express a probability that the next customer will pay with a credit card as a decimal to the nearest hundredth. So let's write that out as the probability of using credit. So we're looking at how many used credit over the total number of customers here. In the problem, we were told 39 customers used a credit card. Total customers, they did list them out. We had 40, 16, and 39. Let me circle those. 40 plus 16 plus 39 was the total number of customers. When you add up all of those in that denominator, we get 95 total customers that they had in the last week. And using our calculator, 39 divided by 95 gives us 0.41052, on and on and on. We're rounding to the nearest hundredth is 2 decimal places. The third says let it rest. So our probability in decimal form for the next customer to use a credit card would be 0.41 or 41 hundredths. In number 3, we have a table of information to help us answer this probability question. Let's look into it. In a class of students, the following data table summarizes the amount of sleep of students and whether they have an A in the class. What is the probability that a student chosen randomly from the class is a student who slept 6 hours or less and who does not have an A? So in our table here, let me use the highlighter. Of those that have an A, there were 7 students who slept more than 6 hours, 4 students who slept 6 or less hours. Likewise, we have students who do not have an A. There was 5 who do not have an A, but they slept more than 6 hours. And then there's 14 students who do not have an A, but slept 6 hours or less. Do you see how that's arranged there? I could add up all of those in the center there. The 7, 4, 5, and 14 would tell me the total number of students. I could add up an entire column of all the students who slept more than 6 hours, or the column of all the students who slept 6 hours or less, or across the rows, add up an entire row of students who have A or do not have an A in the class. We're looking for the probability of a student who slept 6 hours or less. I'm going to use some notation here, less than or equal to 6, just shorthand for myself, and does not have an A. All right, there's our probability. So less than 6 hours is this column. Does not have an A is going to be these 14 students here. We're going to have our less than or equal to 6 hours, not an A in the class, over the total number of students in the class. So we already saw the 14 over, I'm going to just notate for our notes here, we're going to add up the 7, the 4, the 5, and the 14 for our total number of students. So we'll have 14 over 30 is the total number of students there. And when I simplify that fraction, 7 over 15 represents the probability that a student randomly chosen from the class slept 6 or less hours and does not have an A in the class. Let's try again on number 4. In a class, the following data table summarizes how many students have a brother or a sister. What's the probability that a student chosen randomly from the class has a brother? So let's write here, we're looking for the probability of a brother. Let's take a peek at our table. We have has a sister. There are 6 people who have a sister and have a brother. There are 4 people in our table that have a sister but do not have a brother. We have 7 students who do not have a sister but have a brother, and we have 11 students do not have a sister but do not have a brother. They don't have any siblings, right? So for our probability, we're going to look at those that have a brother over the total. How many people have a brother? Has a brother. There's 2 groups here that we're going to add together, the 6 and the 7. It didn't really matter if they had a sister or didn't have a sister. We're only talking about those that have a brother, so I'm going to add both of those in that column, and we're going to have our total. Let's just show it here. We're going to add all of those groups together, 6, 4, 7, and 11. We're going to have 13 over 28, and I cannot simplify that fraction. So 13 over 28 would be the probability in number 4 that I select a student at random and they have a brother in the class. All right, let's look at our next section here. 2 events are called mutually exclusive. If they cannot both occur at the same time because they have no outcomes in common. The probability rule here is if A and B are mutually exclusive events, then when you go to find the probability of A or B occurring, you will add their probabilities together. Whenever you see the word or, I want this or that to happen, I will win the game. If either of these scenarios happen, I don't need them both to happen, just one or the other. I would add their probabilities together. Let's put it in action with number 5. You're rolling a standard number cube once. Let A represent the probability of rolling an even number, and B represent the event of rolling a 3 or a 5. Find P of A or B, the probability of event A or event B occurring. All right, here we go. We're looking for if we roll an even or a 3 or a 5. Okay, standard number cube. So what are my options here? Let's list out the options. So we could have a 2, a 4, or a 6, or we could roll a 3 or a 5 and we win the game, right? Or over all of our total possibilities, 1, 2, 3, 4, 5, 6. So just listing out all the possibilities there, that makes 1, 2, 3, 4, 5 possible rolls to win the game out of the 6 total possibilities. 5, 6. Mutually exclusive. They're not going to happen at the same time. I can't roll an even that is a 3 or a 5 because those aren't the same, right? You add those probabilities together. On our second page, we have that 2 events are overlapping events if they have one or more outcomes in common. So in the last example, I couldn't roll a 3, a 5, and an even at the same time because they were totally separate events. But if they're overlapping, a little bit different story. If A and B are overlapping events, then P of A or B, we're still using or, I want this or that to happen. We're still going to add our probabilities together. Probability of A plus probability of B, but we are going to subtract the overlap. We're going to subtract what they share. Okay, so I'm writing there, subtract the shared. Let me illustrate that for you in number 6. You roll a standard number cube once. Let A represent the event of rolling an even number. Let B represent the event rolling a multiple of 3. Find P of A or B, the probability of event A or event B occurring. All right, so we have the probability of rolling an even, or our second event is a multiple of 3. So let's list those out. I'm going to list them right below. What kind of outcomes are even? We had the 2, 4, and 6. What are the multiples of 3 that are on a number cube? 3 and 6. Okay, let's start with what's the probability of rolling the even? There was 1, 2, 3 possible outcomes out of 6 on the number cube. Probability of event B, rolling a multiple of a 3. There were 2 possibilities out of 6. But what did you notice? What did you notice? We listed 6 in both of those. Let me ask you a quick question. How many 6s are on the number cube? There's only 1. Okay, so I already included 6 in that first event, and I've included it in the second event. I have double dipped on the probability of 6 happening. Apparently now 6 has a double chance. No, 6 has just as much chance as any other number on the number cube. So we double dipped on that 6. So we've got to go back and subtract that overlap. Think of it another way. If I listed it out, what are the possibilities that work here? 2, 4, 6, multiples of 3, 3, and I've already counted 6. Okay, so let's go finish our probability here. When I add and subtract fractions that have a common denominator, we keep that common denominator, add or subtract the numerators up here. So 3 plus 2 is 5, minus 1 is 4. What did I list out over here in green? 4 possibilities on the die. So let me just simplify this fraction. We have a 2/3 chance on a number cube of rolling an even or a multiple of 3, if that's going to let me win the game. Let's try it one more time with number 7. There's a spinner with 15 equal areas numbered 1 through 15. If the spinner is spun one time, what is the probability the result will be a multiple of a 2 or a multiple of 5? Multiple of 2 or multiple of 5. Just going to list it out here for us. Multiples of 2 on a spinner with 15 sections. We could spin a 2, 4, 6, 8, 10, 12, or 14. Multiples of the 5. 5, 10, 15. Okay, so let's find our probabilities of each. The probability of spinning a multiple of 2, there was 1, 2, 3, 4, 5, 6, 7 possibilities out of the 15 sections. We are doing the probability of this or that, so I'm adding. There was the probability of spinning a multiple of 5, 3 out of 15. Any double dips? Any that we listed both times? 10. Yep. We didn't list 5 both times. We didn't list the 15 both times. So let's go back to our probability and make sure that we subtract away that 1 that we've double dipped on. The probability of spinning a 10, there's only 1 10. I don't get to double dip on it. I've already counted it once. I don't get to count it twice. So let's do our add and subtract our fractions here, keeping my common denominator of 15. 7 plus 3 is 10, minus 1 gives me 9 out of 15. I could simplify that to 3/5. I have a 3/5 probability of spinning a multiple of a 2 or a multiple of 5 on this spinner. Next vocabulary here, 2 events are independent. If and only if the occurrence of one event does not affect the probability of the second event. They are independent, separate, don't influence each other. Your probability rule down here says in the box, if A and B are independent events, then the probability of A and B happening together, we do what here? It's equal to probability of A times probability of B. We're going to multiply. If you want 2 things to happen together, I have to roll this and spin that to win the game. I have to have those 2 happen together. I multiply those chances together. Let's use number 8 here. We have a red number cube and a blue number cube that are rolled. 8 says, what's the probability that a blue 5 and a red even are rolled together at the same time? So probability of blue 5 and a red even. Okay, what's probability of rolling a 5 on the blue number cube? There's only one 5 out of 6 sides. We want this and that to happen together. We want both of them to happen together. So we're going to multiply with probability of rolling an even, 2, 4, and 6, 3 chances on the 6 number cube. When you multiply fractions, you multiply across the top and across the bottom. So we have 3 out of 36 or 1 out of 12 probability of rolling a 5 and an even on those 2 number cubes. Again, if you want them to happen together, we multiply. Okay, next thing, 2 events are dependent if the occurrence of the first one does affect the probability of the second. The rule is we're still wanting the probability of this and that to happen, so still going to multiply, but we're going to make sure that when we look at the event B, it's after A has occurred. Let me give you an example here. Number 9, a bag contains 8 red marbles, 4 blue marbles, and 2 green marbles. If 2 marbles are drawn out of the bag, what is the exact probability that both marbles drawn will be red? So we want the probability of 2 reds here, a red and a red. We are taking them out. It did not say I was putting them back in. So let's talk about the probability of drawing the first red. There are 8. Out of how many total? 8, 4, and 2. We have 8, 9, 10, 14. Okay. I want this and this to happen together. Multiply. What's the chance that my next marble is going to be red? I already took one out and put it in my pocket. Going back to the bag, how many reds are left? 7. There are only 7 red marbles now in the bag for me to go and draw. How many total marbles are in there now? Because there's another one in my pocket I already took out. How many marbles are in the bag? 13. Now multiply. Okay, so we're getting 2 reds out. I took the first one out, and when I go back in, there's 1 less red, 1 less marble. So make sure you're mindful of that. Okay, so when you multiply fractions, multiply across the top and across the bottom. Using my calculator, the 14 times 13 is 182. And check to see if it'll reduce, and it does, to 4 over 13 is the probability that I've got this bag of marbles and I'm drawing out 2 red marbles. Let's try again on number 10. A bag contains 8 red, 3 blue, and 5 green marbles. If 3 marbles are drawn out of the bag, what is the exact probability that all 3 marbles will be green? So we want a green, and then another green. I'm going to put them all in my pocket, not putting them back. So probability of the first green there was 5 out of how many total? 16. Added up all of our marbles there. We want these all to happen together. Okay, so multiplying. I already took a green out. There's only 4 green left and only 15 total marbles left in the bag. Go for a third green. There's only 3 greens left and only 14 total marbles left. So let me grab the calculator. Multiplying across the top, we're going to get 60. Multiplying across the bottom, here we go, 3,375. On the calculator, check to reduce, and it does 4 over 225. Let me just show you that really quick. So on your calculator where I multiplied and then I got my fraction here, the 60 over 3,375, it instantly will give you that reduced fraction, okay? Last little bit here, I've got to mention it. It's in your standards. The law of large numbers. Okay, the law of large numbers states that as the number of trials or experiments increase, the average of those results will grow closer and closer to the expected value. The more times I do a probability event, like drawing marbles, the more trials or experiments that I do, the closer and closer it will get to the theoretical probability. In other words, as our sample size increases, the average of the observed results will become more and more representative of the true value. Like flipping a coin, heads and tails. If you flip it a handful of times, maybe 10 times, heads or tails, it's probably not going to occur 50% of the time. But if I made you do it 1,000 times, we would get closer and closer to that true, like 50% probability of a heads or a tails. Okay. All right, friends, that is our probability events lesson. There's a lot of pieces here that are review, but it is okay if you have forgotten. We have refreshed starting way back in middle school, talking about theoretical probability. That examples 1 and 2. 3 and 4, we're still doing the same thing, just kind of unique how we set it up in the table, and you're pulling the information from the table. Now, it might be one little section of the table that we need, like in number 3, or we might have to add an entire column or row. Just make sure you're looking closely at those problems. You also in middle school look at mutually exclusive events. If you want this or this to happen, we add them together. Now, algebra 2 is where we get into the overlapping. So page 2, where we added, but then we subtracted the overlap. That's algebra 2. So we did some review at the beginning to refresh you on probability. The overlapping was your algebra 2 content. And then independent events, if you want this and this to happen together, multiply them. And then again, we're getting into that algebra 2 when they're dependent. Make sure you're observing after the first event has occurred. So if I'm pulling marbles out of the bag, make sure you're observing, okay, I took one out. Did I take away one of the colors that I'm looking for next? And I definitely took a total marble out. So, and then, like I said, the last thing, the standards mention understanding the law of large numbers. The more times I flip that coin, the closer it's going to actually be to 50%. Okay. Let me know if you have questions, guys. I'll see you in class. Have a fabulous day. See you later.